Hello, guys. Welcome back to Learn the Concept. This is the session 5 of our series where we deal with managerial statistics using R. Today, we will be talking about t-test and ANOVA. So, t-test and ANOVA are basically uh, statistical ways to compare the means across different samples or different groups and see whether the groups are similar or different from each other. We will learn that in detail, but before that, we would uh, we should actually learn the concept of what is a parametric test versus a non-parametric test, right? So there are two kinds of statistical tests. One is parametric. So t-test and ANOVA fall under the parametric test bucket, and another is non-parametric, right? There are other tests, for example, Mann-Whitney U test, the Kruskal-Wallis test, and the Wilcoxon-Signed-Rank test, etc., which comes into the non-parametric. So parametric tests are the tests which assume that the data is normally distributed. The data on which the test is being run is normally distributed, whereas non-parametric tests do not have any such assumptions on the data and they are more robust in that way, right? However, t-test and ANOVA are some of the most commonly used tests in managerial statistics, and hence we would definitely like to, pay due attention to these tests and understand how to run these tests, how to interpret the results, etc. Right? So starting off with t-test, it's a parametric test. As we talked about, there are three types of t-test: one sample t-test, two sample t-test, or we also call it test of independence, and paired sample t-test. Right? So one sample t-test is basically used when we want to determine whether the mean of a sample is equal to the mean of the population or not. Right? So, for example, if we draw a sample from amongst all the 10 standard students and their score, and we list their scores, right? Whereas we know that the population mean English score is 76, right? The question that we want to answer using the one sample t-test is that is the sample mean equal to the population mean, right? So we call in this library tidyr. We move on to the one sample test. The one sample test, the null hypothesis is that the sample mean is equal to population mean. Very simple, right? The alternate hypothesis, therefore, is that whether the sample mean is not equal to the population mean, right? So, like I talked about, one of the t-test being a parametric test, one of the assumptions of the t-test is that the data should be normally distributed. So, to check that, we run the Shapiro-Wilk test on the scores. Okay. So what is the scores first of all? Uh, just a second. So we have recorded the scores of a sample of students here, right? And those are the score numbers. Now I want to check whether the scores are normally distributed or not, right? So I will run the Shapiro test on top of that. So Shapiro test gives us the result of p-value is 0.3816, right? Now we already know that the null hypothesis of the Shapiro test is that the data is normally distributed. And since the p-value here is much greater than 0.05, we fail to reject the null hypothesis here, which means that the data is in fact normally distributed and we can run t-test on that. So the way to run the t-test is simply t.test, which is a function already present in our. We will give the data and we will say mu is equal to 76. Mu is nothing but the population mean that we already know to be 76, right? So let's run this and see the results, right? Okay. So these are the results. What we would like to concentrate on is the p-value. The p-value is 0.4533, which is higher than 0.05, which means that we fail to reject the null hypothesis. And if we remember, the null hypothesis here is that sample mean equal to population mean, which means that this sample's mean is actually equal to the population mean, and there is no statistically significant difference between the population and the sample, right? So this is how the one sample t-test works, right? Now moving on to the two sample t-test, independent two sample t-test, right? These are used in situation where we want to compare the means across two groups. So suppose we want to compare the test scores of boys and girls and check if they're statistically different or not, right? So we have a list of test scores from boys and a list of test scores from girls, right? Now, again, since we are trying to use a t-test, which is a parametric test, we have to run the check for normality of the data. We will use the Shapiro-Wilk test here on both the distributions, boys as well as girls. So when we do it for boys score, we see that p-value is 0.43, which is greater than 0.05, which means that we fail to reject the null hypothesis, which means that it is normally distributed. Similarly, for girls score, the p-value is 0.76, which is greater than 0.05, which means that we fail to reject the null hypothesis, which again means that it is normally distributed. Also, in case of uh, independent sample t-test, we need to check whether the variance is equal between the two groups or not. So for that, we need to use the Levene's test, or we could simply use the variance.test, right? This function here. This is also an assumption of t-test that the variance between the two groups should be equal. So we run the variance test. The ratio of variances comes out to be 0.45. P-value is 0.2848, right? Here, the null hypothesis of the variance test is that the variance ratio between boy score and girl score is equal to 1, right? Which means that now, since the p-value is 0.2594, we actually it's 0.2848 here, right? So any which way it is greater than 0.05, which means that we fail to reject the null hypothesis, which means that the variances are equal, or the ratio of the variances is actually equal to 1, right? So variances are equal, we could go ahead and use the t-test here. And once we run the t-test, we see that the p-value is 0.2594, which is again greater than 0.05. The null hypothesis here was that there is no statistically significant difference between the boy score and the girl scores. We fail to reject the null hypothesis, which means that the two means are statistically equal. The mean scores of boys and girls is equal, right? So this is the independent sample t-test. Uh, we call it independent samples because we do not expect any dependence between the test scores of boys or the test scores of girls, right? These are completely different data sets, and we are comparing and to see whether these are equal or not statistically. The third type of t-test is called as the paired sample t-test. Okay, so the paired sample t-test is basically we are talking about related samples or the same sample before and after an activity. So, for example, if a pharma company wants to check the efficacy of their blood pressure medication, um, and they record the BPs of the patient before taking the medication and after taking the medication and record it like so, we could use the paired sample t-test to make sure that to make sure statistically that whether there is a actual benefit of taking the medicine on the blood pressure or not, right? So again, same thing, Shapiro test we have to run to see that the before and after medication data values are normally distributed, and they are, right? Because it's 0.4248 and 0.9236 p values, so fail to reject the null hypothesis. Then we run the t-test with an extra parameter which just to specify that it is a paired sample t-test. So we say paired is equal to true, right? P value here is coming out to be 0.001265, which means that we reject the null hypothesis. The null hypothesis here was that there is no statistically significant difference before and after taking the medicine. And so, therefore, we say that there is, since we're rejecting the null hypothesis, we conclude that there is a statistically significant difference between these two. Okay, so these are the three types of t-tests. We will cover the ANOVA parametric test in the next video. So stay tuned. If you like the content, please Like the video and subscribe to our channel and stay tuned for further videos. Thank you.